Hello! In today's video, I'm going to talk about static, cranking, and dynamic compression. Now I've gone over some of this before, but when I was talking about the camshaft test I want to get run, I got an interesting message from a guy that said it's not going to run, that I am killing the dynamic compression, and without more static compression, it just won't work. And that's really not true. So let's kind of go over this. Now, static compression, as we know, is the actual measured space against the closed space, the volume of the piston when it's down to the volume of the piston when it's up gives you a ratio. Now, this is a standard Cadillac 500, and so it's not very high. Static is probably about 8.2 to 1. When I calculated that, I used a general CC for the head because I have not actually CC'd these heads, and they can vary slightly, but it's never been milled, and that's probably pretty close. It might be just slightly different. But static is 8.2 to 1. So one of the first things I want to talk about is cranking compression. Now remember, when you're turning over a motor, you're only at maybe 150 RPM or so, maybe not even quite that. And so you don't have a lot of air movement. And so during that time, this closing point will affect your cranking compression. And so the PSI you see, if you were to put on a gauge and crank the motor over, is what cranking compression is. And so on a regular motor, I ran the numbers. I went to Wallace Racing and just punched in the numbers and got what I got. Now, your numbers might be a little different. You do got to remember, I'm at about 7,000 foot up. So it does affect what we do up here. Now, static is 8.2, and cranking comes out to about 118 psi, and I think that's pretty accurate. I don't remember. I think I ran a compression test on the motor when we were first making it go. That would be on the other YouTube channel, my name with Cadillac added, for the Cadillac group when I was building the Make It Run motor. But I am going to test this and see on the dyno so that it's the same power going to the starter, it's the same cranking speed, it's the same thing on the same day basically. So we will double check that, but I think that's a pretty accurate number for us up here. On the new cam that I'm going to put in, that drops to 95. And you're like, oh wow, you lost like, 22 pounds. You lost a lot of pressure. Yes, but a Cadillac engine is a big motor and a big piston. And actually, a lot of times, even in stock condition, they are hard to turn over. The starter has to be in good shape. Everything has to be properly grounded for it to work correctly. So this could actually help us a little bit because it should be easier to turn over. And I will double check because I think the dyno, even at that very low RPM, when we're just cranking, will give us an RPM. So if that's true, which I'm pretty sure it is, I will check what kind of cranking RPM and what kind of pressure we have on the dyno with both cams to double check this and see if we drop to this 95, and to see if that 95 allows the starter to turn the engine over better. Now, the dyno will do a little better than it would in the car because it's a much bigger starter. And so it'll go easier, and it might actually show it better than it would if I just tested it in a vehicle. So anyway, we will see how that goes with cranking compression. And like I said, the idea that this, changing the closing, will affect the motor is certainly true at 150 RPM. You have no inertia. Remember, the motor is run on inertia ramp. And our goal in swapping the camshaft is to increase the volumetric efficiency. So the problem I have is about dynamic compression. Now, I ran the numbers on that, again using the Wallace calculator, and going from the static 8.2, even the stock cam drops down to 7.67. And so that's technically, according to the dynamic compression, what we actually have to run on. Now, if you do the same thing with the new cam, we drop down to 6.71. And this is why he's saying it's not going to run. Well, we've gotten too low. But that's not really a realistic number. We are trying to fill the cylinder better when this is running. If you look at the stock motor and you say it's 85% volumetric efficiency. Now remember, we just did a video on volumetric efficiency. If we say this one is 85%, and I'm not even sure it's quite that, it might be only 82. I have seen stocker motors, because this fill isn't great, I have seen them be as low as 80% volumetric efficiency, even though the Z is 0.84. But we're going to call it 85%. So if we take 85%, remember, that's how full the cylinder is getting at peak torque. We're not even talking here. We're not even talking up here. We're talking peak torque. Peak volumetric efficiency is going to be about 85%. Well, that means the cylinder is only going to be full about 85%. And so that is going to have a bigger effect on what compression the motor is actually going to produce. How tight it's going to squeeze all of that air before it actually lights it off. And that'll be in like PSI. It'll be lower down here. It'll be lower up here. It is peak torque is when it's going to hit 85%. But if we just figure 85% of the volume, we actually drop down to 6.97. That would be the compression. That would be at peak torque. That would be how much force we have. And that number makes a lot of sense, because one of the things in the Cadillac world that has come up is the late model head is like 120 cc chamber. And the early model head is like 76 cc chamber. And if you put the early head on a late motor, you wind up at like 12 and a half to 1. Static compression. And so with that, you wind up with a high numeric static compression. So you would think that that motor would be a lot of problems. And yet, there's been a lot of guys that have done this swap with just Starker motors. Now, we're not talking something that has a cam. We're not talking ported heads. We're not talking about a built motor. We're just talking about taking a stock 300 horse motor that is running at 85% volumetric efficiency and swapping that onto it. Well, what your dynamic compression winds up at with only 85% is like 9 to 1. And remember, the reason it's called dynamic is because it changes. It changes depending on how well the cylinder is being filled. And you also have to remember that when you throttle a motor, when you close the throttle, you're at cruise, you're just barely open. Well, you are stratifying the charge going into the cylinder. So the amount of air that's getting squished down is way less. And so technically, during that time, your compression, the PSI that you're generating when it comes all the way up, is way low. And so you shouldn't really have a problem with any kind of dynamic compression, because normally the motor will run even with a lot less. We do it all the time. We throttle motors on the freeway, we throttle motors at idle, they all run just fine. And that has a lot less air going into it. Dynamic is just that, it's dynamic. It is changing all the time. And its main thing that is actually controlling it is volumetric efficiency. What controls volumetric efficiency is inertia ramp, the speed of the air coming in. So I'm expecting to go from a volumetric efficiency of 85 that's only giving me almost 7 to 1 at peak torque. I'm expecting to go up to 100% and use the entire 8.2. So dynamic compression is not what you think it is. This does not affect the motor when it's running. This does not affect the loss of power at peak torque because it's controlled by inertia. It is not controlled. This is not endlessly pumping out. If it was, there'd be no point. We'd close up here. You can't go by the closing point and expect that to be your dynamic compression. Well, I have a 12 to 1 motor, but I put in a big cam, so it's actually a lot less. Well, no, that's not how it works. When it gets cranky, when it's at wide open throttle, when it has good volumetric efficiency, it will fill the cylinder and you will be at your full compression ratio. And that's how this goes. So I actually expect it to get higher. I mean, we're going to increase cylinder pressure. Whenever you increase power, you increase cylinder pressure. If you increase cylinder pressure, you have a better chance of detonation. And that's part of what I'm trying to test. Now, I can't really test that easy on a dyno because we have a coolant system and we are in a controlled environment. So it's really hard to really tell for detonation, but I can see if it's more sensitive to timing. I can do a couple of things to see if this is going to be a problem. But the dynamic compression is not going to be a problem because that is not what I'm going to be at. I am not going to be at 6.71. That calculation is strictly about that closing point, and that is not true. I am going to be at 8.2 if I can get this cylinder to fill 100% at peak torque. And that's my goal. And so that's dynamic, static, and cranking compression. They are correct about cranking, but that's also not necessarily a bad thing. Most people don't understand dynamic at all, and that's part of the reason I just did this video. So I hope that helps. If you need a better explanation, let me know. But a lot of people need to realize dynamic is not as straightforward as just the closing point. That is not how it works. So I wish you well on your projects and have a good day, and I will talk to you later. Bye.